Welcome everyone to this recorded lecture intended for Math 206. And in this lesson, we're going to study the fundamental spaces of a matrix. So basically, um, the fundamental spaces of a matrix are subspaces associated to a given matrix, and there are four of them. In fact, we already have learned two of these four spaces. So let's recall, if you have an m by n matrix A, associated to this matrix are the following subspaces. Number one, we have the column space, which is basically the span of all the columns of A. So you take all the columns of A as vectors, and then you consider the set of linear combinations of these columns as vectors. Then that subspace is what we call as the column space. Another uh, way to think about the column space is that if we think of the matrix A as a linear transformation from Rn to Rm, then the column space of A is identified as the range of this matrix transformation. Okay, so the column space serve as the range. The range will tell us whether a given mapping is onto or not, or surjective or not. Another space associated to A is the null space, right? The null space of a matrix is basically the set of all solutions to the homogeneous linear system Ax is equal to 0. We know very well that um, um, the solution set to a homogeneous linear system like this is always a subspace, and that is what we call as the null space. Now, if we think of the matrix A as a matrix transformation or as a linear transformation from Rn to Rm, recall that the null space of the matrix A is basically the kernel of the linear transformation. And why is the kernel important one more time? It is because the kernel will determine whether the mapping T sub A is going to be one-to-one or injective. Recall that this mapping is one-to-one if and only if the kernel contains only the zero vector. In fact, we have established the relationship between the column space and the null space in terms of their dimensions. Um, the relationship is explicitly stated in the rank nullity theorem. The rank nullity theorem states that if you have a linear transformation T uh, from some finite dimensional space, then the the rank or the dimension of the range plus the dimension of the kernel is always fixed, and it's equal to n. In the context of a matrix A, since the range is the column space and the kernel is the null space, then it follows that the dimension of the column space plus the dimension of the null space is n. This being the rank and this being the nullity. So we are now ready to define the four fundamental spaces associated to the matrix A. So just like before, um, one of the four fundamental spaces associated to A is the column space. The other one is the null space. So basically, we already know 2 out of 4 fundamental spaces of A. Now, what are the other two? The other two may be obtained by simply considering the transpose of A. Now, recall that if A is m by n, the transpose is going to be of size n by m. So in other words, as a linear transformation, if TA goes from Rn to Rm, the transformation associated with the transpose is going to happen from Rm to Rn. Okay? So we can take the column space of the transpose of A. But because upon doing the transpose of A, the rows becomes columns and columns become rows. So the column space of the transpose is basically the span of the row vectors of A. And this is why this space is what we call as the row space of A. So technically, the row space of A is just the span of the rows of A if we think about them as vectors in Rm. And because the rows are the transpose of are the columns of the transpose, then it's equivalent or equal to the column space of the transpose. While the other the fourth fundamental space to talk about is the null space of the transpose of A. So in linear algebra, this space is what we call as the left null space of A. And we shall see later why it's called as the left null space. But basically, the null space of A transpose or the left null space of A consists of all the vectors Y, so that when A transpose is applied to Y or multiplied to Y, it gives us the zero vector. So basically, the left null space is the solution space to the homogeneous linear system A transpose Y equals 0. Now observe that in computing the four fundamental spaces, the first two, which are the column space and the null space of A, they are computed using the matrix A. So technically, we're going to do a Gauss-Jordan algorithm applying to A, no, to get bases for the column space and the null space, while both for the row space and the null space, the left null space, because they both involve the transpose of A, they are calculated by doing a Gauss-Jordan algorithm or a row reduction on the transpose of A, just to let you know. To differentiate between um, rows and columns, sometimes, no, the rank of A, or is basically the dimension of the column space, is what we call as the column rank of A. Now, this dimension tells you how many columns of A are linearly independent. Okay, on the other hand, the dimension of the row space is basically the rank of A transpose. And it's what we call as the row rank because it tells you how many rows of A are linearly independent. Okay, so let's get some example. So find the four fundamental spaces of the matrix A as you can see. So as you can tell, the matrix A is quite special. Um, Simply because upon observation you can see that both the second row and the third row are just multiples of the first row. So yeah. Um, so if we're going to do a Gauss-Jordan reduction of A, we find that the RREF is the following matrix. So basically, uh, the second row elements are just zeroed out. Also, to get the other two spaces, we have to look at the transpose of A. So the transpose of A is this 3 by 2 matrix. And then upon doing Gauss-Jordan reduction, we see that only the first row remained. The other rows are just zeroed out. So what does this mean? So for the column space of A, this pivot indicates that only the first column um, will serve as a basis for the column space. So in other words, if you take this column that will serve as a basis and the other two columns are just redundant. So the column space of A is one dimensional, so we can say that A has a column rank of 1. On the other hand, to get the null space of A, we solve Ax equals 0, or the homogeneous linear system Ax equals 0. But upon solving, if we take this as the variable x1, x2, and x3, we see that the variables x2 and x3 are both free. So if this vector is found in the null space of A, then that means to say that looking at the first row, well, let's write x1, x2, x3 first. This one is equal to Looking at the first row, we see that x1 is equal to 2x2 plus 3x3 by simply equating this to 0, putting all of these terms to the right, right? And then x2 is free, x3 is free, so we just copy them as is. So as you can see, we can write this as a linear combination of the vectors 2, 1, 0 plus 3, 0, and 1. And this is why the null space of A is the span of the vectors 2, 1, 0, 3, 0, 1. So the null space is in R3. Yeah, we know that very well because A is a 2 by 3 matrix. As a transformation, it goes from R3 to R2. Nasa loob ng R2 yung column space ni A, while nasa loob naman ni R3 yung kanyang null space o yung kernel. Okay? Now, to get the outer two spaces, we now look at the matrix A transpose, right? So what is now the row space of A? The row space of A is basically the column space of A transpose. So we look at the columns of this and we find a basis for the span of these vectors. By looking at the RREF, only the first column contains a pivot, meaning to say this is the only row that matters. The other will be redundant. So the row space of A, or the column space of A transpose, is basically the span of the first column, which is 1, -2, and -3. And similarly, finally get the fourth fundamental space, we get the null space of A transpose. So we look at this, we try to um, solve this homogeneous linear system. This is your homogeneous linear system. This corresponds to the variable x1, and this corresponds to the variable x2, where x2 is free, right? Um, so we find that x2 is free variable. So if this vector represents your typical vector in the null space, in the left null space, then x1, x2 is free, so we'll just write it down. While x1, when you look at the first row, equated to 0. Um, it's just x sub 2 one more time, right? So we can write this as the multiple of 1, 1. So basically, the left null space or the null space of A transpose is the span of the vector 1, 1. So what do you notice? This is one-dimensional, two-dimensional, one-dimensional, and one-dimensional. So these are the four fundamental spaces of the matrix A. Now to visualize what's happening, no, in pictures, I have plotted all of this information geometrically so you can have a visual understanding of what's going on. As you can see, both the null space of A and the row space are subspaces of R3, while the column space and the left null space are subspaces of R2. On the left, you can see the space R3, where it contains the null space of A. The null space of A is spanned by 2, 1, 0 and 3, 0, 1. So you can see here the vector 2, 1, 0 and 3, 0, 1. It spans they both span an entire plane, which is colored in pink, right? While the vector 1, -2, -3, which form a basis for the row space, is one-dimensional. So here it is. Here is that vector, and it spans a one-dimensional subspace. So that's the row space of A. Okay. On the other hand, for the other two subspaces, in this case they are subspaces of R2, the column space is generated by the vector 1, -1, while the left null space is generated by the vector 1, 1. So here in this picture is the vector 1, -1, and this is the column space of A. While this is the vector 1, 1, so the subspace is spanned by 1, 1 is the left null space of A. Now remember that at any point in this video, you can pause, no, if you want to um, have a minute to absorb all the information. So you can just pause and stop for a while if you need to rest. Okay. So the question or the main question will be, how are these four fundamental spaces of A related to one another? If you look at the picture, now if you look at the picture, um, yeah, one thing that you can notice is that uh, because the vectors 1, 1 and 1, negative 1 are orthogonal to one another, you can check that their dot product is 0. So the vectors are perpendicular, therefore the subspaces themselves are orthogonal, meaning they are a pair of lines that make a 90-degree at the intersection point, which is the origin. On the other hand, when you look at R3, this is the null space and this is the row space. So, okay. So the null space, it's a plane. No, while the row space, it's a line. It's not visually obvious, but you can check that the line or the row space of A, the blue line, is actually perpendicular to the entire plane. You can take a look at it, no? And you can verify it algebraically by taking the dot product of these two vectors. You see that their dot product 301 dot 1 negative 2 negative 3 is going to be 3 plus 0 minus 3, so it's 0. And the dot product of 210 with 1 negative 2 negative 3 is also 0. So meaning to say, this vector is perpendicular to that vector, and this vector is perpendicular to that vector. Although we cannot see it visually because of our limitation, because we cannot move this around. No. Yeah, but you can check through GeoGebra that they are actually at 90 degrees with the blue. The pink vectors are at 90 degrees with the blue vector. Therefore, the plane that they generate is at 90 degrees with the blue line. Did you understand? So if we're going to ask how are these four fundamental spaces related, so maybe by looking at this example, um, we can infer that orthogonality is an important part, right? So we are now going to answer how are these four spaces related through the idea of an orthogonal complement. Now, if you have a subspace, you can take it's what we call as the orthogonal complement of that subspace. What do you mean by the orthogonal complement of a subspace? So, first of all, you can take the orthogonal complement of any set, even if it's not a subspace. Okay, so let's take a non-empty subset S of Rn. We can define the orthogonal complement of A as the subspace as the set denoted by S perp. Now, ang basa dito, we read this as S perp. The word perp came from the word perpendicular. Okay? It is defined as the set of all vectors orthogonal to every vector in S. So imagine you have a set of vectors in S. So you're going to look at all the vectors that make a 90-degree angle with S or that are orthogonal with S. Yeah. So those are the vectors in S perp. Now what can we say about um the set S perp? Now first of all, I have some remark. Now remember that S here is just an arbitrary non-empty set. So S in the first place may not be a subspace. But when you take the span of S, the span is obviously a subspace. According to this remark, if the span of S is W, no, then um, S perp is the same as W perp, meaning to say every vector that's going to be orthogonal to the vectors of S are also orthogonal to all the vectors in the span of S. Why? Because let's say, for example, no, S contains V1 up to Vk, so that W is the span of S. So meaning to say W is maybe k dimensional or less. It depends on the linear independence of these vectors, but definitely whatever the span is, it's going to be a subspace. No? If if let's say a certain vector v is orthogonal to every vector in S, meaning if v dot vi is 0 for I starting from 1 to k, we're going to show that this vector v is orthogonal to every vector in this span. So if we take, well, let's say a linear combination C1 V1 plus C2 V2 CK BK VK, let's say it's an arbitrary vector in W, no? Then you can check that if I take the dot product of V with this linear combination, this is basically in the span, right? If I take this dot product, using the property of that product, you can play around with some algebra, yeah, like this. So the dot basically distributes to every term. And because of this condition, it's orthogonal to every vector in the list. So all of these dot products will be 0. And that's why, ang gaya nga ng sabi ko, kapag ang vector ay orthogonal sa lahat ng elements ng S, it's going to be orthogonal to every vector in the span. And you know what is its consequence? The consequence is that S-perp is always going to be a subspace regardless, right? Yeah, you can check. Now you can check that S-perp is going to be a subspace all the time. Okay? Definitely, most definitely, if S is in the first place a subspace, then its orthogonal complement is also going to be a subspace. The way I want you to think about orthogonal complement is as follows. Let's say you can imagine W as a subspace in R3 na lang, so we can imagine it. So let's say W is a plane, a two-dimensional plane as pictured. Now W perp, how does it look like? So to get W perp, you're going to look at the vectors that are perpendicular to every vector in W. So the way I want you to imagine that it simply looks like a straight line passing through the origin, of course. And this line is going to make a 90-degree angle to every vector in W, in the sense that if I take, let's say, an arbitrary vector over here, let's say this is a vector V, no, then let's say this is a vector Wi, let's say it's in W, then by the orthogonality, you can check that these two vectors are at 90 degrees. Now, that's what we mean by the orthogonal complement W perp. So let's take a look at some example. So number one, if A is any non-zero vector and we take S to be the set containing A, so your set only has one vector in it, how do we describe S perp? Well, in the case when n is equal to 3, let's say, nasa R3 tayo, if n is equal to 3, if you only have one vector in your set, let's say this is your vector A. Oh, wait. So let's say this is your vector A. So where are all the vectors that make a 90-degree angle with A? So obviously, that's going to be a plane, an entire plane. Of course, this plane has to be infinite, right? Sorry. Medyo hindi maganda yung, oh, ba't pa siya nagiging bilog? Anyway, let me just draw the plane for you. It's going to be this plane. right? So this is going to be your S perp, or the perp of the singleton. Did you understand? But in general, if you are in an n-dimensional space, the perp of a single vector is the hyperplane orthogonal to A. How? How do we know? Because if we take A to have components as shown, A1 up to AN, then a typical vector x1, x2, xn is in S perp precisely when its dot product with A is 0. No? So if you take this as your vector x, for example, so that means x dot A has to be 0. And if you perform this dot product, it gives you this equation. Okay, and you know very well that we call this hyperplane orthogonal to A. Okay, so that's it for this example. The next example, we will illustrate the case when your set only has two vectors in it. So let us say V1 is the vector 1, 1, 3, and V2 is the vector 2, negative 1, 3. Let's say you are asked to find a basis for S perp. So we know that S perp is a what? Is a subspace. But how does it look like? What is its dimension? Those are the questions that we would like to ask in linear algebra, right? So what do we do? So to do this, we take an arbitrary vector in S perp, let's say V. We know that this vector V is in S perp precisely when V is orthogonal to both V1 and V2. Being orthogonal means its dot product with V1 and with V2 are both 0. But if we try to place variables for the components of V, let's say x, y, and z, this being orthogonal to V1, meaning the dot product of these two has to be 0. So what's the dot product? The dot product is x plus y plus 3z, right? And it has to be 0. Also, if this and these are orthogonal vectors, so their dot product is 0. So if I take the dot products, that 2x minus y plus 3z is equal to 0. So what we're really forming is, yeah, a system of linear equation. In fact, a homogeneous linear system, which is what we know. We have to solve this by the Gauss-Jordan algorithm in order to find S perp. So we apply the Gauss-Jordan algorithm. So we eliminate the 2 in the 2, 1 position. So we eliminate this using this operation. So this is what happened. Okay. And then we're going to make a pivot on the second row by multiplying the second row by negative 1/3. In effect, we have this matrix. Again, you can pause this video and uh, take your time, no, to do the computations here on your own. Then using this pivot, we're going to zero out that one by applying this type 3 operation. The result is this, and now we are in RREF. So therefore, what do we have? So V is in S perp precisely when. So the free variables are, there's only one free variable, and in this case, it's Z, right? That's why I did not change Z anymore. If you look at the first row, this means x plus 2z is equal to 0. So x is negative 2z. That's why here you get a negative 2z. When you look at the second row, that means y plus z equals 0. Solving for y is minus z. That's why you have a minus z. So all the while, the vectors in S perp are just multiples of this vector. And this is why we take S perp to be the span of the vector negative 2, negative 1, and 1. What can we say about S perp? Well, it's one-dimensional. It's a straight line. Yeah? So if we take a look, now as you can see, V2 is not really a multiple of V1. Yeah, it's not a multiple. That's why yung set V1, V2 is LD. This is why if we take the dimension of W, which is the span of S, we should know that that space is two-dimensional. So the span of S is basically a flat plane, no, containing this vector. So you can imagine, let's say this is 113, this is um, example lang ito. This is not drawn to scale. No? Now these two vectors will generate an entire plane. You can imagine it like that. Medyo ayusin natin yung drawing. Now where is S perp? S perp is the straight line. Here's your straight line, right? It's a straight line in the direction of -2, -1. So you can imagine this as your S perp. Tapos maybe the generating vector is right there. It's at 90 degrees. You can check. Now you can check that this is orthogonal to that and this is orthogonal to that. You can do that. Okay? That's what's happening here. Hopefully you did understand. So if you're looking for a basis for S perp, of course, you have to write it as a set, the set containing the vector -2, -1, and 1. Okay. So right here, I sketched pala on a certain angle. Ito yung positive x-axis, positive y-axis, and this is the positive z-axis. At a certain angle, you can view it like this. Ito yung V1 at ito yung V2. Of course, hindi ko na drawing yung plane that contains them, but there's definitely a plane that they generate, right? What's more important to see here is that the generating vector that we have obtained is perpendicular to both of these vectors. Hopefully you can imagine that the red vector is perpendicular to the two black ones. And therefore, the span is going to be perpendicular to the plane, or the line is going to be perpendicular to the plane. Okay? So we did this for two vectors. What about, let's say, we have k vectors in the list. So to generalize, we will be needing the help of matrices. So what we do is if we have a list of k vectors, we consider the matrix A containing these vectors as as its columns. So we will put all of these as columns of a matrix A. The size of the matrix is now n by k. So each of these are n dimensional and then there are k of them. So k columns all in all. Okay. So as you can see, S perp, no, is basically the set by the previous remark in the definition. Whenever you are orthogonal to S, you are orthogonal to the span of S. That's why if I take the perp of S, well, the span of S is the column space of A, right? So if I take S perp, that's going to be the perp of the column space. Okay? So now what does it take for you to be in S perp? Well, you are in S perp precisely, a vector V is in S perp precisely when its dot product with each one of these is 0. I from 1 to, mali ito. This has to be K. I from 1 to K. So if you are perpendicular, so if you take a look at this, no, if I put coordinates or components to V, let's say x1, x2, xn, and imagine this as your A, ito yung V1. Now, you think of this as your V1, ito yung V2, ito yung Vn. We're saying that this vector dot this vector is 0. This vector dot this vector is 0. This vector dot this 0. This vector is 0 also. So to express that, what we do is we instead write these columns as rows. How? Um, well, we take the transpose of A. If we take the transpose of A, this column has to lie down as the first row. This column has to lie down as the second row, and this vector has to lie down as the last row. So if you do this matrix multiplication, you see that we're doing dot products. And each time the dot product is zero, so what's left here is an n-dimensional zero vector, right? So what is this equation? This equation is basically A transpose times V is equal to zero. Now what do we know about the vector satisfying this? They are found in the null space of A transpose, which is what we call as the left null space of A. Again, why is it called a left null space? Wait a minute. So I'm going to explain. Okay, to explain why the left null space is called the left null space, um, well, remember that a vector y is in the left null space of A if and only if A transpose, sorry, times y is the zero vector, right? And this zero vector has size, if A is m by n, okay, if A is m by n, um, A transpose is going to be what? N by m, right? So, and y here has to be in Rm, right? Y here has to be in Rm para ma-multiply yung A transpose sa kaliwa. Okay? So this is like you have an n by m times m by 1 equals an n by 1 thing. Okay? Now, what you do is you take the transpose of both sides. If you do the transpose of both sides, what do we get? What we get, property of transpose, you know that doing transpose of every term reverses the order. Y transpose A equals 0 transpose. So meaning, yung zero, yung mga vectors nyo ngayon are now row vectors. So when you take a look at this, you express this in terms of components. Ito yung components ni Y. Nakahiga na siya na ganyan. And then this is your original A. Yan yung A11, A12. Okay? A1N, AM1, AM2, AMN. Then what results is 0, 0, 0, 0. M lahat yan. So this equation basically is equivalent to this equation. So what you do, if you do this dot product, you get 0. You do this dot product, you get 0. You do this dot product, you get 0. And this is why we call it a left null space, because the vector is on the left, no, of the matrix. Yun nga lang, it's they call this, it's lying down as a row. But anyway, instead of having y transpose times A equals 0, we will normally have A transpose V or Y equals 0 instead of the, yeah. Just explaining why the name is called left null space, because the vectors are multiplied to the matrix on the left. So what did we learn here? We have learned that V is in S-perp if and only if V is in the left null space. In other words, this is equal to the left null space. So the perp of the column space is the left null space. When you take a look at our previous slide, so where is that previous slide? One more time. Wait a minute. I'm just going to look at that illustration. Where's that? Ayan, okay. Here, as you can see, this is the column space of A or the range of the transformation, right? It's the range of the transformation. And the left null space is this left null space. As you can see, they are at 90 degrees. So we have established really why the column space and the null space are always orthogonal as subspaces. Yeah, so that's what we have established here. Okay, and we now state it as a theorem. So let A be a given matrix, then the orthogonal complement of the column space is basically the left null space. Okay, while the orthogonal complement of the row space of A is just the usual null space of A. Okay, why do you think number 2 is also true? Why if you take a look at our previous diagram, no? Ito naman yung dalawa. Where are they? Yan. Nandito naman sa R3 yung dalawa. Ito yung row space. Ang perp niya is the null space, which is an entire plane. See? Yeah? Well, we can... Well, the proof of number 1 is already in the previous slide, but why is number 2 true? Well, in number 1, you can just replace A by A transpose. Because if you replace A by A transpose, equation 1 now reads the following: A transpose transpose. But what is A transpose transpose? A. And of course, yung column space ng A transpose is the span of the columns of A transpose. Is basically the span of the rows of A. And this is why the row space or the orthogonal complement of the row space is the null space. So we have established these relationships. Okay, so we have now answered the first question. Now, we're now going to talk about some more properties of orthogonal complements, but in order to establish those properties, there are some things that we need to explain first as lemmas. Okay. Um, First of all, let A be an m by n matrix. Lemma number 1 states that if you have obtained a matrix B from A by doing a sequence of elementary row, a finite sequence of elementary row operations, then their row spaces are actually the same. So meaning to say, the span of the rows of two matrices are the same if you have just obtained one of the matrix from the other by performing elementary row operations. Why is that? Well, by doing row operations kasi, there are only three types of row operations, right? Either you interchange two rows. Now, this means row I gets interchanged with row J. And when you do this, do the span of the rows change when you rearrange the vectors in a set? No. Also, if I multiply, let's say, a certain row by a certain multiple, let's say C, no? So, na-replace siya by some multiple. Do you change the span? Not really, kasi you're just extending one of the vectors in its direction by a certain factor, or either maybe shrink or put it in the opposite direction. So the span do not really change because what matters is the direction in the span. Okay, and finally, um, when you do a type 3 operation, this is where we replace the row I by its sum with another row vector. Well, what you get is just a linear combination of already existing rows. So this vector is still in the span. I mean, you're still in the same row space. And this is why when we do elementary row operations, we do not really change the row space of a matrix. And as a consequence, if let's say you take the RREF of A, the row space of A is the same as the row space of its RREF. Okay? Now, we're now going to explain number two. Number two, let's read number two. The rank of A is the rank of A transpose. Know very well that the rank of A is what we call as the column space, while the rank of A transpose is what we call, mali, column rank, and the rank of A transpose is the row rank. So in other words, lemma number two says that the row rank and the column rank are the same for any matrix of any size. If let's say the row rank is 5, then the column rank is also 5. Meaning, if you have a maximum of 5 linearly independent columns, there will be a maximum of 5 linearly independent rows as well. And why is that? Why is that? You just consider the RREF of A. As I remember, the rank of A transpose is the dimension of the row space. And what is the dimension of the row space? Well, we do row reductions, right? So we count the number of pivots in the RREF of A as well. So that will also tell us how many rows are linearly independent. And basically that's also the rank of A. And it proves statement number 2. Now that we have this information with us, we are now ready to prove or to explain the main result of this uh, part of the lesson. So if you have a subspace, so basically the theorem is telling us some information about the orthogonal complement of a particular subspace. Okay, so let's say W is a subspace of Rn. Number one, the only thing that can be found in both the subspace and its orthogonal complement is the zero vector. Whenever the orthogonal complements intersect, they can only intersect at the zero vector. Okay, that's why from our previous examples, if you have a plane, now let's say the orthogonal complement is straight line, and the only intersection in that of this the line in the plane is the zero vector, nothing more than that. Okay, number two, when you add dimensions together of W and its orthogonal complement, it completes the dimension of the space. So let's say dito nasa R3 tayo, no? Nakita nyo, this is two-dimensional while the dimension of W perp is 1. So if you add this together, you get the dimension of the entire space. And this is mainly the reason why the word complement was used. They are complementary in terms of their dimensions. In other words, if one is a small space, the other has to be big, right? If W is small, the perp is big. If W is already big, the perp is small. Yeah, that's why they are called orthogonal complements. Well, number three tell us that if one is an orthogonal complement of the other, then it happens vice versa because the orthogonal complement of the orthogonal complement is the same space where it began. Now, property number three, it looks very simple, no? Yeah, it looks quite obvious, but the proof is not that easy, as you will see. In fact, most of our work so far was done in order to prove statement number three, which is rather obvious sana, kaya lang, it's not really trivial. So let's explain. Let's begin with uh, number one first. Okay, why do W and its orthogonal complement intersect only at the origin? Well, to see this, Let's take any vector x in the intersection. We know that intersection of two subspaces is non-empty. It's a subspace, so we can take an x there. Then, if x is in the intersection, it is both in W and W perp. Meaning to say, x is in W, x is in W perp, but the vectors in W perp are orthogonal to the vectors in W. What does that say? It meant to say that x has to be orthogonal to itself. Therefore, if I take the dot product of x with itself, it has to be 0. But you know x dot x is the square of the norm of x. This means that the norm of x itself is 0, and that will imply that the vector itself is 0, proving that the only thing living in the intersection is the 0 vector. Okay? Remember that you can always pause this recording if you want to write down something. Okay? Okay. We're now going to prove, yeah, the conclusion is that the intersection only contains the origin. We now prove equation number 2, but before we prove this in general, we take a trivial case. The case when W is the trivial subspace. If W contains the 0 vector, of course, every vector is perpendicular or orthogonal to the 0 vector. That's why its perp is Rn. Because this is 0-dimensional, this is n-dimensional. Obviously, when you take the sum of their dimension, it's always n. It's n, right? So that proves the claim for this trivial case. So for the rest of the proof, let's assume that W is non-trivial, meaning there are more vectors in W aside from the 0 vector. If that is the case, then the dimension of W has to be positive. So meaning we can get a basis for W, let's say with D elements. We set D to be the dimension of the subspace B at W. Okay. Because W is basically the span of these vectors, no? So what we do is we put these vectors as columns of A, and obviously the subspace W has to be the column space of A. Okay? If I take the perp of W, it's the perp of CA, and by the previous lemma, by a previous result, no? Ano na-prove natin? Na-prove natin na ang orthogonal complement of the column space is the left null space. So by the rank nullity theorem, if I consider the nullity of A transpose, that's the dimension of the left null space, right? Kasi, okay, the dimension of W perp is the dimension of the left null space of A, which is the nullity of A transpose. But by the rank nullity theorem, now remember, si A po ay, ano bang size ni A? M by D. Okay? Which means A transpose has to be, sorry, this has to be D by N. So the number of columns of A transpose is N. So maghahati yung rank and nullity sa N. So if we know the nullity, what is the rank? N minus the rank of A transpose. But you know what's the rank of A transpose? Hmm? By the previous result, once again, it's the same as the rank of A. Now what's N minus the rank of A? Applying the rank nullity theorem one more time. Well, it's N minus D, right? Kasi yun yung dimension nung ano pala, nung W, because W is D-dimensional. So yung rank ng A, which is the dimension of the column space, is D. Okay? But what is D? Yun po yung dimension ng W. So meaning, nagko-complement din yung dimensions ni W perp tsaka ni W together. So when you add them together, the sum is N. That proves statement number 2. Okay? And to finish up the proof, we now have to prove statement number 3. We have to prove that the orthogonal complement of W is the same space W. So what we do is we take an X in W, an arbitrary vector X in W. You know, by definition of W perp, no, it means that for all vectors Y in W perp, its dot product with X is 0. Consequently, dapat orthogonal si X sa lahat ng vector na nasa W perp. Okay? Yes? Because it's dot product. So si X is basically in the perp of W perp. So what did we prove? We proved that whenever X is in W, it's in the perp of W perp. So this means that this set is a subset of that set. To prove the equality, to prove this equality, if A is a subset of B, para mag-equal sila, we have to prove that B is a subset of A as well. Okay? So if we apply the previous result, which is statement number 2, to W perp, so we will not apply it to W, instead doon sa W perp. We know that the dimension of W perp plus the dimension of the perp of W perp has to be n as well. Which, by the way, is the same applying number 2, statement 2 again to W. It means the dimension of W plus the dimension of W perp has to be n. So we now have these equations. So what we do is we can cancel this on both sides. You're left with the conclusion that W and the double perp, no, space have the same dimensions. Because W is contained in the double perp of W, they have the same dimensions. What do we know about this? Properties ng mga subspaces to, right? If W is a subspace of, let's say W2, and their dimensions are the same, actually, this is telling us that they are not actually different to one another. The truth is, they are the same. We have a theorem about this before. Yeah? So that concludes that they are equal. Okay? And we now have proven this. So that's why yung theorem natin kanina that states that the orthogonal complement of the column space is the left null space. Okay? And the orthogonal complement of the row space is the null space. Using theorem number 3, ito number 3 dito, we can also say that the complement, orthogonal complement of the left null space is also the column space. Wala nang ibang panggagalingan. And the orthogonal complement of the null space is basically the row space. So this now also holds. Okay? So at this point, pwede na nating sabihin two subspaces are orthogonal complements of one another. It now makes sense kasi nga ang complement ng complement ay yung sariling subspace lang. Okay? And as an application of these relationships, no? We will be talking about the matrices of the form A transpose A and AA transpose. No. For now, it doesn't look clear bakit natin pag-aaralan yung dalawang matrices na to, but we will be needing these two forms of matrices in the future lessons or in the next few lessons. That's why we're going to explore about the properties of these matrices. And in fact, we can say something nice about their fundamental spaces. So to give you an idea first, let's do it in one example. So given that A is as follows, it's a 2 by 3 matrix, so A doesn't have to be square, remember? So let's multiply A transpose times A. So what's A transpose times A? So we put A transpose right here, 1, 2, 2, negative 3, negative 1, 1. Let's put A over here. Okay, let's do the matrix multiplication. So this is row 1, column 1. 1 plus 4 is 5. Okay, what else? Row 1, column 2 is 2 minus 6 is negative 4. Is that correct? Tama ba yun? And then we can check my multiplication is if it's correct. Okay. Negative 1 plus 2, it's 1. Okay. Then we'll do this. Second row, first column, 2 minus 6 is negative 4. And then 4 plus 9 is 13. Negative 2 minus 3 is negative 5. Hopefully it's correct. Negative 1, third row, first column, negative 1 plus 2, it's 1. Third row, second column, negative 2 minus 3 is negative 5. And second row, third row, third column, 1 plus 1, it's 2. So this means A transpose A has to be the square matrix. Okay, as shown. Notice anything? First of all, the product A transpose A is a square 3 by 3 matrix. Well, it's kind of evident because we came from a 2 by 3. Kaya kapag A transpose A, yung 2 by 3 maging 3 by 2 multiplied by 2 by 3. So nagiging 3 by 3. Okay? Second, do you notice anything weird or not really weird? Anything special about this matrix? Yes, no? You can pause this if you want to try to guess, no? But the answer is that when you look at this, anong tawag natin sa matrix na pareho? Yung nasa taas ng diagonal tsaka nasa baba ng triangular. Symmetric, na? Yan. It's worth noticing. In fact, it will be symmetric. Why? Kasi if you take the transpose of this, regardless of A, actually, regardless of A, doing the properties of A transpose, you get something like this. Remember, we're reversing the order. And notice that the transpose it is itself. And hindi naman nakakabigla na symmetric talaga yung A transpose A. Now, let's do A transpose. This time si A naman ay naririto. Nandito naman yung A transpose. Okay, let's do the dot product. First row, first column, it's 1 plus 4 plus 1, it's 6. First row, second column, 2 minus 3 minus 1, negative 2. Is that negative 2? Tama ba? 2 minus 3. Ay, mali. Ano ba? 2 minus 6, negative 4 minus 1, negative 5 pala. Okay. Okay, let's do second row, first column, 2 minus 6 minus 1, negative 5 pa rin. 2 minus 6 minus 1. Yeah. And then second row, second column, 4 plus 9 plus 1, 14. As you can see, AA transpose is now a 2 by 2 matrix. Hindi naman nakakagulat din yun, no? And it's also symmetric. Using a similar logic to the previous one. Yeah. So these are some of the things that we have observed about same thing, no? Kasi if you take transpose of AA transpose, you also get this as a result. You get A transpose still. Okay. And aside from they are symmetric, notice that when we do this product, what we're taking here, no, here, are actually the columns of A. So there are three columns of A, right? Ito yung first column, second column, third column. Ngayon nga lang, row na kasi naka-transpose. First column, second column, third column. And because this is matrix multiplication, we know that upon doing entry by entry, we're doing dot products. So what we do is we're taking the dot product. So yung ij entry nito is the dot of column I and column J. Column I of A and column J of A. Notice? And on the second product, this time, ito naman ang ino-operate natin, right? And they are now the rows of A. Kaya nga yung ij entry mo dito naman, notice that it is the row I of A dot the row J of A. So basically, pinapakialaman naman natin yung rows ni A sa una, yung columns ni A. So tandaan niyo ito, yung A transpose A has something to do with columns of A, with the columns of A. It's related to the columns of A, while yung AA transpose, it's kind of related to the rows of A. Okay. Do you notice that? Yeah. In general, these matrices are symmetric matrices. So this is what we have observed. If we denote by kappa j, the column j of A, j from 1 to n. So, sabihin yung column 1, kappa 1, column 2, kappa 2, and so on and so on. Forth. Then, the matrix multiplication definition tells us that the ij entry of the product A transpose A is basically the dot product of the column I and column J. So this is how it will look like in general. And this is the reason also why the matrix has to be symmetric, because dot products are symmetric, right? The other hand, if we now consider the rows of A and we label them as row I for row I for the row I of A, I from 1 to M, then the ij entry of the product AA transpose is the dot product also of row I and row J. That's why we can see that AA transpose is like this. Okay. Now let's talk about the four fundamental spaces of these matrices. So it turns out that for a given matrix A, regardless of the size, the null space of A transpose A. So here in this theorem, we talk about A transpose A, okay? So the null space of A transpose A is just the null space of the base matrix. I mean, kung saan ng matrix ka nang galing, hindi nagbabago yung null space. So in other words, pag pinapatay ka ni A, pinapatay ka rin ni A transpose A. And vice versa. If you are getting killed by A transpose A, meaning nag-zero ka when it's multiplied, pinapatay ka rin ni A. Ganun din. In fact, yung row space ng A transpose A is not really different from the row space of A. Yeah, that's the consequence. But for the column space, it's a little bit controversial because the column space of A transpose A is not the column space of A, rather, it's the column space of A transpose. But what's the column space of A transpose? It's the row space of A. But I prefer not to write this anymore kasi para hindi kayo maguluhan, na. Mas magulo kasi pag in-introduce ko yung column space ng A transpose like this. Eh sir, ba't hindi nyo kinonsider kalaba four fundamental spaces? Why did we not consider the fourth subspace, which is the, what do you call that, the left null space? Kasi po, yung left null space, kukunin mo yung transpose nung nasa loob, right? Bago mo kunin yung null space. But, you know, A transpose A is symmetric, kaya parehas lang siya dito. Kaya as you can see, tatlo lang yan. Wala na yung pang-apat. Kasi parehas lang dito yon. Okay? Now, for the details of the proof, no, I would like you to refer to our online lecture notes that can be found in, what do you call this? In our class website. I don't want to spend time uh, here in the recording, no, to minimize the time required. So, yung details naman are in full, no, doon sa ating lecture notes, so you can have this as reading assignments. So basically, ang pinaprove dyan is number 1, and then number 2 will follow as a consequence, and number 3 will also follow as a consequence. Um, and just like before, if you replace A here by A transpose, replacing A by A transpose, ano mangyayari sa theorem na ito? Mangyayari ganito na siya. It now talks about, suddenly it now talks about AA transpose. So the null space of AA transpose is the null space of A transpose. The row space of AA transpose is the row space of A transpose. While the column space of AA transpose, it's the column space of A. Remember, A is being replaced by what? A transpose. You know what do we have as a corollary? Hmm? These are the corollaries. So let me explain. So the truth is, when doing A transpose A, or maybe AA transpose, you do not really change the rank of the base matrix. If you're, let's say the base matrix is A, you found that its rank is 3. Regardless, no, yung A transpose A tsaka AA transpose will also have ranks equal to 3. Did you understand? And by the rank nullity theorem, because the nullity is determined whenever you determine the rank, we can say also the same thing for the nullity. Whenever you know the nullity of A is, let's say, 5, no, the nullities of A transpose A and AA transpose are both 5. Question, why are these true? It basically follows from the last portion. Kasi po, when you do the, well, yung rank ni A kasi, tignan natin ha, yung rank ni A kasi ay parehas sa rank ng A transpose. Did you remember this property? This is the dimension of the column space of A transpose. But the column space of A transpose is the column space of A transpose A. So it's the rank of A transpose A. Using a similar argument, just like here, no? Yan. Papatunayan nyo rin yung number 3. Yung rank ngayon ng AA transpose is the dimension of the column space of AA transpose. This is the dimension of the column space of A, which is the rank of A. Kaya nga ito, tsaka to, pare-pareho. And by the rank nullity theorem, you apply that, you will see that the nullities will also will not also follow to be equal. You know, if there's one thing that we have learned about all of this, no, we have learned the following unifying idea. Meron tayong unifying theorem, but it talks about square matrices. You can think of this as like unifying idea in the case when A is not square. No? If A is not square, these are the things that is going to be equivalent. Why are they equivalent? It follows from the previous theorems. Let me explain. So, what are the statements that are equivalent? Yung AX equals B mo, A here may be non-square, okay? Ang claim natin is at it has at kasi pwedeng inconsistent ito, right? It has at most one solution. Kung meron man isa lang, na, it has at most one solution for any B. Kailan daw mangyayari yun? If the null space of A is trivial, meaning ang solution lang sa AX equals 0 ay 0. Number 3, if the columns are linearly independent. Kasi nga po, yung column rank mo o yung simple yung rank is full. No, ibig sabihin, lahat ng columns mo are linearly independent. And that's what this property is what makes everything possible. Yung non-singularity ng A transpose A. Kasi nga po, pag ito ay, ang column space na ito tsaka column space na ito are the same. So, kung non-singular yung isa, yung A transpose A, parang yung mga columns, instead of saying A is non-singular, no? The truth is, um, kasi hindi nga, maaring hindi square si A. The most that we can say about A is the columns are going to be linearly independent. Eh ano naman yung version nito? Pag pinalitan natin si A ng A transpose, this is what we have as an alternative, no? Ganito na yung linear system mo, Y na yung unknown. Here, instead of the null space, we get the left null space of A. And in this case, this is associated to the rows, no? The rows are now linearly independent and that yung matrix na AA transpose is non-singular. Okay? Well, it kind of follows from this theorem. If you want to see the full details, these are some theoretical results that I have to tell you because they will be used in the future lesson. Okay? Okay ba? Ngayon, what can we pick up from these two unifying ideas? Ito yung column versions, ito yung mga row versions. What can we pick up from this? In the case when A is a square, ang mangyayari ngayon, pag square yan, I mean, si A ay square. Pag nangyayari ito, remember, it means A is non-singular. Kaya nga, kapag si A ay square, kapag non-singular yung A transpose A, non-singular din si A, and vice versa. And we therefore, ganun din naman dito. And we therefore have added two more statements doon sa ating unifying theorem. So far, to conclude this lecture, these two statements are now added in the list. So the non-singularity of A is equivalent to the non-singularity of the magic matrix A transpose A. Kasi pag ito'y totoo, according to the theorem, yung mga columns na A ay linearly independent. Square si A, kaya n by n si A. Kung linearly independent, ito na yun. Sorry, yung number 11 yun. Yeah, ito pala yun. Diba? Equivalent sila sa isa't isa. Ito naman, it now talks about rows. Ito naman yun. Diyan siya equivalent. Kaya nga non-singular. Did you see this as a corollary? Ito yata yung unifying theorem yata yung wala sa lecture notes, but hopefully na ipaliwanag ko sa inyo. If you have questions, you can send an email to me kasi this lesson was recorded as an asynchronous supplement for this week. Okay? Thank you very much for your listening. You can just send an email or a chat through MS Teams if you have any questions. Maraming salamat and see you in the next class.